Okay, we're back and we should hopefully see some Sage stuff brewing. So you can actually see that I got a couple tabs open because again, I had split this into a couple different sections. So the first portion of this little worksheet is going to have this discussion of some of this random number stuff. So we're going to look into these two little functions. So we're going to have rand int binomial. So that's going to be kind of our original one. That's going to generate some of these. I guess I shouldn't say it's the original one. This is going to be my original one, which is going to generate those things from 0 up to our bound b. And then the one that we're actually going to want to use is the one that then doesn't have a number on it. It's just going to be this rand int binomial, and that's going to be this one that's been shifted backwards a little bit. So in that previous example, this would be the one that generates numbers from 0 to 6. This one would then be the one that I'm going to want to generate numbers from -3 up to a 3. We'll have a couple different ways on how we're going to have to feed these things in. This first one's going to be fed in with that proper upper bound of 6. This one is then going to be fed with that smaller bound of 3. So that's where we get slightly easier arithmetics because those sums are over slightly smaller ranges of things, but they're still going to function basically the same. So down below, just to kind of showcase some of the stuff that I blurred about, in the last video, is that we can obviously generate just classic random numbers or these kind of uniform random numbers inside of Sage with our rand int function. So if I go rand int from 0 to 6, you can see that it's going to print out, 5 or so random numbers. They're going to be great. They're going to be awesome. You can click through this as long as you want to, and eventually get bored of clicking through it. And then at some point, you're like, okay, let's generate a whole bunch to see kind of the nice little distribution take shape. So that's what I got going on down here. So I'm going to have b be my little bound. So it's going to be this 6. So it's going to kick out numbers from 0 up to 6. So it's going to have a list of those 7 things. I'm going to generate 1,000 of them. And then each time I'm going to generate one of those numbers, I'm just going to increase that index value. So if it randomly generates a 3, the index 3 thing inside of this list L is then going to tick up by a 1. And what I should see is a decent amount of uniformity emerge. So you can see that between 0 and 6, they're not all exactly the same. I get 144, 175, 139, and so on. And I think that was what before. That should kick out. If I take 1,000 and divide it by 7, it should be about 142, 143, depending on how you round that. And you can see that we're going to get a little bit of fluctuation. Obviously, if I increase this to, like 100,000, it's going to take a little bit longer. But what you'll start to see is that this will start to stabilize really nicely. Is that once I start seeing these really large values emerge, I'm going to be right at 1/7, almost exactly. If I kick it up to 1 million, well, it's going to generate now 1 million numbers. So we're going to sit here for a second, and you'll see that we're really close to getting it on the money. Again, there's still a little bit of fluctuation, but that fluctuation is pretty stabilized by the time we start generating this number of things. So the second thing is going to be this quest of looking at these binomial distributions. So again, this tails that are going to be a little bit smaller and more of the bulk hanging out in the middle. There are a couple different ways you can generate random numbers that have the following shape. So it's actually been deemed that this binomial distribution is then going to be the optimal one in this Krystal's Kyber. They did flirt with the idea of trying to use a Gaussian distribution, but then they later found out that the complexity of that wasn't really going to get anything additional. So they, doubled back on just the binomial distribution becomes a really easy way to generate them, and it's totally fine enough as well. So that's one we're going to live with because it's easy to generate them, and we can do them very, very quickly. The first thing is just going to be printing out this exact choosy kind of stuff. So inside of Python or inside of Sage, I have an ability to do this choose command. So it's going to be this binomial of the top number. So that blah choose the second number. So all I'm doing here is just kind of printing out what those numbers should be. So in this kind of ideal scenario. So it's going to be that 6 choose 0, 6 choose 1, 6 choose 2, so on and so forth. And that's going to print out those original probabilities that I had before. So you can kind of see the one way to generate a 0 out of the 64 of them, i.e. about 1%. I have 6 ways, so that's that binomial of 6 choose 1, ways to generate a 1 out of the 64. That's going to be about my 9%. There's 15 ways to make a 2. So again, that's binomial of 6 choose 2, so about 23% of the time, and so on down that little list. So that's going to be what we're shooting for when it comes to actually generating those numbers, is that we'll try to come back and compare those numbers. So that's kind of our ideal scenario, and then we'll auto-generate some to see how close we actually are. So down here is just going to be kind of the same version of let's just generate some of these numbers in that little fashion that we saw before. So all I'm doing here is I'm going to randomly generate some numbers between 0 and 1, and then I'm going to add those 6 things up. So I'm going to add up, so sum 6 entries. So I'm going to have my range of 6, and that's going to then, kick out some zeros, possibly up to a 6. So if we go from there, you can see that my first run, all I generated were 3s and 4s, which again is not unlikely. I know that the 3s and 4s are very common in this little setup. So 3s happen 31% of the times. 4s happen 23% of the time. You can see that between 2 to 4, that's going to amass about 80% of our numbers are going to sit in there. The other 20% are then going to be split between 10 at the 0 and 1s and about 10 at the 5 and 6s. So when I generate these, when I don't see some of those little tail entries, that's totally fine because they're not nearly as likely. When I ran it a second time, you can see that I did get a 0 this time, which gave me, 6 consecutive zeros in my ran in function, which is the only way that we're actually going to generate a 0. I also saw a 1, which again happens about 10% of the time. So if I run this again, didn't get any large numbers there. Got some 5s emerging. At some point in time, you can maybe get a 6. So it took me a few times to actually get a 6, but eventually it will kick out a 6 as well. So that's going to be kind of our cheap little way. So that's just going to be add those numbers up. And that ended up becoming this little function right here. You can see that I just took that statement and it became my return statement. So feed in the bound for whatever you want that upper value to be. So if I wanted to go between 0 and 6, then use that function with that nice little 6 argument. The second process is then going to be that other way of sliding it back a little bit. So what's going to happen here is that my bound is going to be a 3. So what I'm hoping to see then are going to be these numbers between -3 up to a +3. I guess before I do that, let's run this section because I realized I didn't actually ever run it, just to kind of showcase the other one does in fact work. So here I'm just running it 1,000 times, and hopefully this printout of percentages should be similar to our exact one as well. So I'm not using the function here. I'm still just kind of hand coding what that's going to be. So it's going to print out those little beasts. And then again, if it kicks out a 4, increase the thing at index 4 up by a 1. So you can see that in about 1,000, we get pretty close. So 1%, 10%, 20, 34, 21, 10, and then technically like a 1.7. So maybe a couple more 6s than I would have expected, but still pretty good. If you increase that up to about 10,000, again, you should get closer and closer to those exact values as well. Okay, so now when I come back to this little bottom part, what's going to happen here is that I'm going to kick my bound to a 3. So here I'm going to generate numbers between -3 and +3. The way that I'm going to generate those is going to be through this little command like here. So if I run that, what you'll see is that it's going to generate things from -3 up to +3. Officially, what I've done is I've actually taken 2 of the other ones and then just subtracted them, but I combined them into one single sum function. So what's going to happen is that you're going to randomly generate a number, and then you're going to subtract it from another number right off the bat, and you're going to do that 3 total times. So you're going to see something minus something. So again, the range that you could have there would be -3 up to a +1. Because you could have 0 minus 1, you could have 1 minus 1, or you could have 1 minus 0. So you can quickly see that individually those little ranges are going to be between -1 and +1. And then if you do that 3 times, you're going to start to see that flex out. So instead of being from -1 to 1, you're going to go all the way from -3 to 3. So you're going to see that kind of cheap little subtraction bit on the inside. So previously we did not have that, and now I'm going to add that thing in. And then I'm going to drop that bound down by a 3 as well, or down by a factor of 2. So we switch it over. So again, that sum runs half as often as it did before. So if that bound was, 6,000, this one only has to run 3,000 times because I'm chopping it in half. I'm generating the same number of random numbers. I'm just doing 2 at a time rather than doing them all individually and then subtracting them as well. There's a couple other kind of funky things in this block of code down here, just because it's going to generate numbers between -3 and +3. What I wanted to do is I wanted to still store those into a list. So what I've basically done is I've taken the -3 and I'm putting that into the 0 bin. So I'm just shifting everything over then. So that's what's happening here is that I'm just basically going to add that little b value. So when it generates a -3, it's going to put it in the 0 bin. When it generates a -2, it's going to put it in the 1 bin. And then at the end, To make it print out nicely, I'm just going to subtract off that b. So it's going to say -3, which is currently living in index 0, is going to have this number of occurrences. So if you generate it like that, if I run this a whole bunch, you should see basically the exact same distribution that we had before, but a slightly different way of actually generating those things. And if you go back to the top, you'll see that that's going to be its separate own little function. That's the one that we'll use over and over and over again in that next section, is that when we generate these little S's and E's, what's going to happen is that those individual entries that are going to come from it, we're going to want those to be generated via this RAND-int binomial distribution. So I'm going to have lots of things that are going to be very small, kind of centered around 0, but then we're going to allow some of those little tail entries to emerge as well. Not a ton of them. Obviously, if we have too many of them, then these vectors are going to have too long of a length, and it's going to break some other stuff, but we're going to allow just a couple of them to be small. And that's where that little function is then going to come into play. You could, again, take this original one, and then before you send it back to the user, just subtract off the bound value, which shifts it. But it's customary to then do it in this kind of subtracty way, just because there's less entries in that little sum. So I'm going to pause it here. We're going to jump back into the notes land. We're going to talk a little bit about matrix multiplication via polynomial multiplication. Actually, the other way around. We're going to talk about polynomial multiplication done via matrix multiplication, as well as some of the new twisty little bits that we'll need as we move forward. So I'll pause it. We'll switch back, and we'll go from there.